Okay, so the next thing we want to talk about when we think about measurements and observations is just a little bit about the kinds of statistical tools and the data analysis that we might use to help understand these observations. And the key sections of Wunsch to keep in mind are the Appendix A for this, which covers a lot of these topics in more detail than I'm going to talk about here. There are also lots of other references, including my math notes, which I've linked to from the homework one. So, we've got this huge ocean. It's vast, it's diverse. We're interested in robust and representative observation. So the robustness comes from when the observed quantity is measured with a known accuracy and precision. That is, the signal might exceed the noise. And what noise is really up to us to define, and what signal is up to us to define. But we are talking about making measurements of some signal that exceeds the noise, and therefore we can get an accuracy and a precision associated with that set of measurements. The representativeness of an observation is maybe a little less familiar unless you have been trying to think about how you measure something as big as the ocean or as old as the ocean. And that means that you are taking a measurement that is not a misleading, anomalous state of that particular phenomenon. So you don't want to average together distinct events that are different unless you are averaging over everything that happens in a year or everything that happens at a particular location over a particular range of time. So you're trying to represent the underlying variability in the correct way, or at least maintain some control over that. So robustness and representativeness are two things that you want to keep in mind, and that's what we're going to talk about a little bit. So the thing that you always learn in, probably learned in elementary school, when you make a measurement, it has an accuracy and it has a precision. So here's an example for conductivity, temperature, and depth sensors. So it measures temperature, salinity. It actually measures conductivity, but you can infer salinity from that. Pressure. And so the temperature is measured to within about 2 milli-degrees centigrade. That's the accuracy. And the precision is actually higher. So that means that the variability can be measured at about a factor of 4 more precisely than you can get an accurate measurement of a temperature, a particular temperature. Similarly for salinity, you have an accuracy and you have a precision. These are kind of useful guidelines. Pressure about 3 decibars, which is about 3 meters in the vertical. And so and oxygen is about 1%. Here you go. But these are often not the issue we have. The issue we have in ocean sampling often has more to do with representativeness than it does to do with accuracy and precision. This is plenty accurate and precise. The bigger problem is that there are lots of things in between where you happen to be measuring, and that's part of what you wanted to describe. But if the instrumental error is random, then repeated measurements can be averaged to obtain a more robust measurement of the average. So, here's an example. Here's a time series, and then here's the probability density function. If you have not seen probability density functions, it's probably good to pause now and go check out what that means on Wikipedia or Wolfram Alpha. That's an important concept. This basically means, so this is showing eastward velocity, this is showing northward velocity. They both look kind of Gaussian, they're spiked in the middle, they're pretty symmetric. So you would say, oh, here's the signal, I can take lots of measurements, and if I took an average, the average would be, the more measurements I average, the more it would close in on this most likely value. And here's the wind speed, which is interesting because this is related to the velocity, but it's, sum of the squares. It has a different PDF. Why does it have a different PDF? Well, look, there are negative numbers here and negative numbers here, but speed is a positive definite thing. So you're actually getting a quite skewed PDF because of the definition of wind speed. So when we make algebraic manipulations of things that have an underlying probability distribution, you end up with a different probability distribution for the function that has the results of the function that's been applied to it. That's a nice idea. Okay. If, however, we do have a Gaussian, a normal distribution, then we know lots and lots about things. The Gaussian looks something like this. 68% is within plus or minus 1 standard deviation. 95% in this one, in 2 sigma, and etc. So this, a measurement out here is extremely unlikely. A series of measurements on here is even more unlikely than a single measurement. One thing you can do is you can make 2 PDFs and just evaluate to what extent their tails overlap. Or you can make an error bar with a 1 sigma error bar or a 2 sigma error bar and see if the error bars of 2 different distributions overlap. If they do, that gives you a hint that there's some possibility, some pretty reasonable possibility, that they might be overlapping. You can get much more precise than that, but for our purposes right now, that's probably good enough. Okay, if I take the average of this quantity, the average is going to be more narrowly peaked than the original distribution. In fact, the standard error, that is the uncertainty in the average, should decrease as the square root of n, where n is the number of independent observations that are averaged together. So if we're repeatedly sampling from a distribution like this, the uncertainty in the error is decreasing every time we sample like the square root of n. So if we want to detect a signal, we have to have the expected standard error be below the signal magnitude. What does that mean? So here are some examples of different PDFs, all clustered around 0. And then this green one over here is a nice example of one that probably is detectably different from 0. These 3 differ in their standard deviations. This one differs in both its mean and standard deviation. So we could pretty confidently say that the mean of this distribution, the mu here, is non-zero. A closely related concept to the probability density function is a probability distribution, either way you think of it, is the expectation value. That's when so if you take one of those PDFs and integrate it over all values or sum it up if it's over all discrete values, then you'll find 1 that says that the probability of finding it at some value is 1. It exists somewhere. The average or mean of the thing, so this is the probability of finding Q at a particular value, Q prime. The average or mean is just you multiply that probability times the value, and then you run over all the possible values. So the things that are more probable are more heavily weighting in this. The things that are less probable are receiving smaller, and the things that are at 0 probability don't affect this at all. You do this, you get the expectation value, the theoretical average or mean. All of those are equivalent of this. If you did this with a function, you get the mean of a function. So this is kind of what we said before, that the PDF of a function doesn't have the same distribution, but you can find aspects of the PDF of the function by using this operation of multiplying the function times the probability distribution of the argument of the function. And that gives you things like the mean. I could have also done the variance. I could have done the standard deviation by putting different functions in here to assess what their typical value is through this expectation value operation. The most used probability density function is the Gaussian or normal distribution, which here it is. It looks like a quadratic up here, but it's an exponential to the minus quadratic. Then it has a normalization factor, which satisfies this. And so here's the mean, and here's the variance, which relates this sigma and this m or mu to the properties of that function. So you might wonder whether oceanographic data is normally distributed. We saw some examples of winds where they were approximately, and then the wind speed where it wasn't. So velocities often have long tails to one direction or the other. That's typical of turbulence. Sometimes they are exponential or log normally distributed. Analog instrument errors are usually pretty normal. Digital instruments, not so much. But here's the important thing. There's something called the central limit theorem, which means that if you take repeated observations of any variable drawn from the same distribution over and over, then the standard error of the average converges to a Gaussian distribution. That's called the central limit theorem. Let's say that a little bit more mathematically. The central limit theorem states that given certain conditions, the mean of a sufficiently large number of independent random variables, each with a finite mean and variance, will be approximately normally distributed. The central limit theorem has a number of variants in its common form. The random variables must be identically distributed. Okay, what does that mean for our measurements? It means the PDF of a particular measurement, say temperature, salinity, velocity, whatever, might not be normally distributed, but the average over repeating that same measurement many times will become normally distributed. So, even if the data is not normally distributed, the average will tend toward normal distributions as the number of independent observations increases. Oceanographic measurements represent an average, like a running mean of time or a spatial average, and so the central limit theorem applies naturally in that kind of an average product. The standard error in the mean or the average, is then estimated to be the standard deviation of the data being average divided by the square root of the number of independent observations. Independent. What do I mean by independent? I mean they are statistically independent of one another. So knowing the value of one set of observations does not tell you anything about the value of another set of observations. We'll come back to that in a second. Now you might wonder, okay, we just average like crazy and then we get a nice normal distribution, but what if our flow isn't average? Like, what are their patterns? And then we're averaging over those patterns. We might be muddying the signal. And so that's where representativeness comes to play. You need to think about whether your observations observe the thing you want, and you need to think about whether there are distinct features being averaged together that shouldn't have been. So there is a whole art to doing this, which is basically called mapping or optimal interpolation, or lots of things like that, where you take a set of observations like this, which are just all over the place, and you come to a map that looks like this. Wunsch discusses this very nicely in the end. We're not really going to use a mapped product or a climatology for this first paper. We're going to use direct measurements, but we will be using a lot of maps and interpolated products later in the class, so it's useful to know what it means. Okay, so how do we figure out how many independent observations we have when we just have like a time series? You can use the autocorrelation function to estimate how distant you have to be before the measurements start becoming independent of each other. So here's the idea. You take a time series of temperature. Now you take every point in this temperature and average it with the points that are separated from it. So you measure two different pieces and you see how correlated this point is with every other piece in it. Then you move to the next one. How correlated is that? Move to the next one. How correlated is that? Then you collect them all together by the separation time between them, and you find a figure like this. Here's the autocorrelation near zero lag. Here's the autocorrelation for everything, but there's this big spike near zero. And it starts at 1. That is, every point in the time series is correlated with itself. And it drops off to close to 0, kind of wobbles around a bit. If we go to this first 0 crossing, that's the first time when this measurement, or a measurement, this separation, this lag away from another measurement has no correlation. So that's a way that you could say all the stuff over there, or maybe if this was very oscillatory or something, you might wait till the oscillations died out a bit to say, I have no more correlated signal. And once I'm out where the correlations have vanished, then I can safely say that those observations are independent of one another, and therefore I take this time lag, chop up the time series, which is 40 years, and I chop it up into 5-month intervals, 6-month intervals, and bingo, I have 80 different independent observations from the 80 different 6-month intervals in this 40-year record. Discussed more in Appendix 7 of Wunsch. A lot of the appendix in Wunsch talks about Fourier analysis, which is a really powerful tool for separating out the contributions to complex signal by separating by frequency or separating in space by wavelength. We're not going to do a whole lot except for when we get to waves at the very end of the class. The one exception are power spectra, which are a really powerful tool. And we've already started talking about how to read them. We'll look at more and we'll read more of them without understanding too much about how they're generated. But it is really easy to make your own power spectra from a time series or from a spatial record in MATLAB using these two functions, p-Welch or PMTM. And so here's another power spectrum, also in time. So this time it's cycles per hour rather than cycles per year. And you can see here's 10 hours over here, and here's 100 hours. One cycle per 100 hours, one cycle per hour. And here's the M2 tide. That's the lunar semi-diurnal tide. And here is the inertial period F. And so these bumps have, this is related to the pendulum day that we talked about before. These bumps stand out from their neighbors as having signal on them. And then there's this overall slope, which basically says slower things have more stuff in them than faster things. This is a comparison between measurements at 3 different depths, and you see interesting distinctions between those. The slopes are different for this kind of background stuff, and then the spikes have different amplitudes, relative amplitudes, which is saying that basically certain tides are more important at different depths in the water column. And then here's our original power series, which is this Hoybers and Curry paleoproxy power series. You're starting to see how this comes together. Okay, one big thing to worry about when you're looking at time measurements is aliasing. Aliasing is what happens when you measure at, say, a particular sampling frequency, but maybe there's higher variability than you measured in that signal. That higher variability just randomly scatters in the resolved part of the spectrum and affects your power spectrum or affects your record. Similarly, if there's slow variations outside of what you can measure, you might have aliasing in the other direction, where you might go back to the same location and measure different signals, even though that was always there. You were just not able to capture the full cycle on lower frequencies. So it's really important when you're thinking about aliasing and time series issues. What do you mean by noise? What are the other parts of the spectrum like? What's the signal you want to measure? What are the time scales associated with these? What are the practical consequences? Like, does your instrument measure that fast? Can it measure that fast? How long does your experiment have to be to get the precision you want? I want to show one quick example of a big mistake in this regard, and I'm going to delete this first. Here is a set of observations from Harry Bryden in a 2005 Nature paper. And Bryden is a seagoing oceanographer, and he had led cruises out to measure the Gulf Stream on the Mariana transport of the Gulf Stream over and over again at a particular location, 25 north, kind of close to where the rapid measurements are. And in 57, he measured it to be 22.9 spheredrops, which is a million cubic meters per second unit. 1981, a little bit smaller. 1982, a little bit smaller. 98, smaller still. 2004, still smaller. on the basis of these 5 measurements, he said that AMOC, the Atlantic Meridional Overturning Circulation, had slowed. That's the title of the paper. And you might say, oh my God, is that a sign of climate change? And in fact, this is one of the predicted changes from climate change, that the AMOC would eventually slow under surface warming and melting of the ice cap in Greenland. He thought he had captured this during his lifetime. So we remember, it's how you design an experiment. Well, how long is this scientist alive? But, and so, this got a lot of press. If you've seen this very excellent and tacky movie, The Day After Tomorrow, this kind of cascading collapse of the meridional overtransport is the thing that happens right before New York is frozen over after a big wave of sea level rise comes and crashes it, and a catastrophic climate change that happens in only a matter of days. But now that we have the rapid mooring, remember I said these are moorings that monitor at 26.5 north, so close to the same location, we can get continuous records. And when we get continuous records, we see that there's about an annual variability, but there's a whole lot of variability. So what happens if you go out every decade or so and randomly sample out of this kind of a distribution? Let's put it side by side and see what we get. Okay, here's the record from Bryden. Those are the records, bing, 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 that he is making the decline argument on the basis of. But when you put it next to stretch to be on the same scale and in time and transport, you can see that actually it wouldn't have been that hard to sample randomly out of this and get a decrease of this amount. This high frequency signal is aliased into these measurements. So it's not so scary when it's seen in context. This level of decrease happens all the time. In fact, it happens pretty much every year. It just wasn't what they were expecting when they went to go make these measurements. Could they have known? Well, possibly. Actually, there was a long record, not at 25 north, but farther south in the Florida current, which Henry Stommel coordinated, which is using telephone cables to infer the measurement of this transport. We talked about this last time. And so now when we go and we look at this long record, and actually it's been extended out to 2018 and 19 now, at Rapid, you can see how amazing this data set is. This is the equivalent of ship after ship after ship making that transect like Bryden did across the Gulf Stream to measure the transport. Those mapping techniques that we talked about similarly could have gaps. This is a temporal gap, but there are spatial gaps as well. So when you hear somebody talking about empirical orthogonal function and infilling using that, or optimal interpolation, or climatologies, these are just mathematical methods to fill in the gaps. You should be skeptical about the way they're used. There's a large literature trying to use these EOFs to glean dynamics by looking for coherent patterns. There's also machine learning based things that are similar, called self-organizing maps, and other machine learning principles which do a similar kind of thing. They don't really necessarily have to reflect something real in the ocean. They could just be a sampling bias, a reflection of the particular data set you're looking at. So they need to do some error analysis when they use this kind of an approach. There we go. Here's an example which is showing that if you didn't have a lot of data to begin with, different mapping methods might give you actually really different answers. Okay, we've talked about the data set types already. And the last thing I want to talk about is the website. On the website, there's links to lots of data. Some of those may be broken, but we will certainly put in more and update as we go. When people find a good one, let me know about it. It's great to add them to here. Some of these are clearinghouses, like the Physical Oceanography Data something, PODAC. That's got a lot of different data sets in it. It's a searchable repository. And so check out these when you're starting to look for where your data is going to be for this project. Thanks very much. See you on Thursday.